Hey guys, Mr. Peterson here. I'm out sick today, and I just wanted to go ahead and record a video because I don't want you guys to get behind where we are. So this is a continuation of lesson 6.1. Here we'll be doing example 2, and in a separate video we'll do example 3. This is example 2, where we are going to apply this new theorem, position from velocity. And the idea is that if you're given the velocity and its initial position, you can predict the future position for all future times by using the initial position and then adding that to the integral of the velocity function. So that's what's going on here. This will give you the position function. Which is kind of what we did on Tuesday, but this is just an alternate way of looking at it. And these kind of situations do pop up on AP tests, so it's important to kind of recognize when this is going on here. So this is example 2. It says position from velocity. A block hangs at rest from a massless spring at the origin s equals 0. At t equals 0, the block is pulled downward 1/4 of a meter to its initial position, which is s of 0 equals negative 1/4, and released. So they just gave us initial position. Kind of a key idea to this one. And you can see a figure of this if you look in the book, but it's just a spring getting pulled down. The velocity in meters per second is given by the function v of t is equal to 1/4 times the sine of t for t is greater than or equal to 0, and assume that upward motion is positive. So we have a we have a velocity function, and we have an initial position. So the first thing we're going to do is look at how we would have kind of approached this on Tuesday. So on Tuesday, what we would have done is we would have thought about, okay, you can probably hear my hound dog barking in the background. That's Ladybird for you. We know that s of t is the same thing as the integral of v of t dt, which we know by just plugging in that the integral or the v of t function is 1/4 times the sine of t dt, and we've also been given the initial position, so s of 0 is equal to negative 1/4. Okay, so as we would have done this the other day on Tuesday, our first step would be to take the integral of this. So remember, down with derivatives, up with integrals. So the antiderivative of sine is negative cosine. So this would be negative 1/4 cosine of t plus c. All right, but we need to figure out what is the actual position function, and since we know initial position, we can calculate that. We know that at 0, if you plug in 0, you'll get out a 1/4. So we would know that negative 1/4 is equal to negative 1/4 times the cosine, and so we need to plug in 0, cosine at 0 plus c. So we know the cosine of 0 is positive 1, so 1 times a negative 1/4 is a negative 1/4. So we get negative 1/4 is equal to negative 1/4 plus c. We add 1/4 to each side, and so we get that 0 equals c. So we now know that the position function s of t is negative 1/4 cosine of t plus 0, but we wouldn't write that. So using this new theorem, we can also get this. Whoa! I have a little bit of a technical difficulty there. I do miss my little cradle for my iPad. I'm trying to use a book here. Using this formula, this theorem, we can say that this would just be the initial position plus the integral from 0 to t of your v function. So what we could do, so we'll call this alternately, and we want to do it two ways because, like I said, this does pop up on AP tests in this kind of form, so you need to be familiar with how to recognize it. Alternately. And on your homework, it is going to ask you to do it both ways. So we know that s of t would be our initial position, which we know is negative 1/4, plus And then we would do the integral from 0 to t of our v function, which is 1/4 times the sine of t dt. Okay, so we have a definite integral here, so we need to use the fundamental theorem of calculus on this. So this would be equal to negative 1/4 plus, so we need to do the antiderivative of this, which we did in the previous version of this. So the quantity of negative 1/4 cosine of t, but we're going to evaluate that from 0 to t. So now we use the fundamental theorem of calculus. So we've got that negative 1/4, carry it down, plus, and so here's our fundamental theorem. It's going to be this minus this, so negative 1/4 cosine of t minus negative 1/4 cosine of 0. Well, we know that cosine of 0 is 1. 1 times a negative 1/4 is a negative 1/4. But since we're minusing a negative, it's going to become plus 1/4. So at this step right here, we have negative 1/4 plus negative 1/4 cosine of t. And like I said, this minus a negative becomes plus a positive. Cosine of 0 is 1, so plus 1/4. You should notice we have a negative 1/4 and a positive 1/4, which will cancel out, giving us our position function, which we already knew, but now we've gotten it a new way, is negative 1/4 times the cosine of t. All right, they also want you to graph the position function over the integral from 0 to 3 pi. That's question B. Graph the position function over the integral from 0 to 3 pi. So, let's sketch maybe our y-axis. We know cosine. This cosine function has been vertically shrunk by a factor of 1/4, and it's been reflected over the x-axis. So we know normally cosine would go between 1 and negative 1, but in this case, that negative 1/4 is going to make it go from negative 1/4 to positive 1/4. So let's make that be kind of our y grid over here, positive 1/4. And we need to go from 0 to 3 pi. So there's 0, there's 1, let's say this is pi over 2, this is pi, this is 3 pi over 2, this is 2 pi, this is 5 pi over 2, and then this is 3 pi. Alright, so let me switch colors here. Like I said, we know normally cosine would pass through 1, but this time it's going to pass through 1/4. And we know the negative out front reflected it over the x-axis. So we're going to start at negative 1/4. At pi over 2, cosine is 0, so we'll be at 0 there. And at pi, cosine is negative 1. So the negative 1 times the negative 1/4 makes it a positive 1/4. And then using what we know about periodic functions, we can just kind of sketch out the rest of it. There we go. Full with sound effects. You don't get that when you're in class. So there is our position function s of t. All right. And then on question C asks, when does the block move through the origin for the first time? Question C, when does the block move through the origin for the first time? Well, we know that that is going to happen whenever s of t is bigger than 0. So when s of t is greater than 0, so it first moves through the origin you'll see that, yes, origin at, if we look at our graph, it's right there, pi over 2. And that kind of makes sense. If you pull the string down, not the string, the pulley down, what is this? A spring. You pull it down 1/4, So you can kind of make sense. We'll be at a -1/4 then, and then it comes up, and then it'll pass through the origin right there. It'll go up to +1/4, and then back through the origin there. And then question D is when is the block at its highest point and when is it at its lowest point? So this is question D. So its highest point would be kind of like we just talked about right there at pi seconds. So the highest point is at pi seconds. I never labeled my axis here. This is seconds, and these are, what are the units for the vertical units? I don't know, I don't see. Oh well, at pi seconds, and then it'll be at its lowest point at 2 pi seconds. Lowest point. All right, so there's that. So that's the first example. Let's we're going to go through example 3 here in a separate video. So there's that, and I'm going to stop the video, and you can look at the second video now.